Alright, ladies and gentlemen, so in this video we're going to start looking at some mathematical modeling as we close up shop on chapter 1. And the goals of this video are to be able to use direct inverse and joint variation in mathematical modeling. We're going to do a quick recap and define what direct inverse and joint variation are first. And we're going to see how we can use some of this information to actually put some real-life application in play to some word problems involving some of these different variations. So first and foremost, direct variation. What is direct variation? The biggest key for direct variation, in my opinion, is that y is directly proportional to the nth power of x. The second thing that you see on that list, okay? And so in my opinion, that's probably the easiest way to think about it. So it's directly proportional to the nth power of x, all right? So as things are changing to x, it is directly affecting, all right, what is happening to y. So three characteristics that show direct variation, and that we're talking about as an nth power. Y varies directly as the nth power of x, all right? It is directly proportional to the nth power of x, and taking those two things into account, we understand that this direct proportion means that if x to the n power is our independent, what's changing, and y is directly proportionate to it, what's going to happen is y is going to be affected by a constant of variation, k in this case, being multiplied to x to the nth power. So how does this differ from a different form of variation? Well, let's take a look as we go to inverse variation now. The following are equivalent, all right? Y varies inversely as x, okay? Y is inversely proportional as x, and for some constant k, I have it hidden right now. So pause the video. Think if you can think of what it would mean if we are focusing for direct variation, a directly proportional equation, what would an inversely proportional equation look like? Well, hopefully we can kind of see and understand that if we're directly proportional, we're multiplying by that product. Well, if it were inversely proportional, we're multiplying it by that reciprocal in this case, okay? And so if we see an inverse variation, it would be k times 1 over x versus being multiplied by x. And then lastly, the one that's probably used a little bit more infrequently is just joint variation. And we deal with joint variation. That means that we have a new variable that we are taking into account, and that both the x and the y are a part of the same variation equation. They are both being multiplied by a constant of variation k. And so we can find ourselves a joint variation when our x and our y are being multiplied by our constant of variation. All right, well, this is all fine and dandy, but I think it's helpful if we start diving into an example as to how and when and why do we use direct inverse and joint variation. The first example I have for you. The distance a ball rolls down an inclined plane is directly proportional to the square of time it rolls. All right, right on off the bat, there's a key word. Right when you see that directly proportional, your mind needs to start thinking, I got to start thinking about those three equivalent statements about direct variation. Now, y directly is proportional to x. So, key phrase. And it's proportional to the square of the time it rolls. Square of the time that it rolls. During the first second, the ball rolls 8 feet. Our goals for this problem are to find out, hey, write an equation relating to the distance traveled at the time, and in the end, how far will the ball roll during the first 3 seconds? All right. Well, first and foremost, we know that we are dealing with directly proportional example here. So I'm just going to go ahead and write down y equals k to the x times n, just so we know what we are trying to be focused on and looking at. All right, but the interesting part about it is now let's take y, let's take x, and let's put that into more of a perspective for our problem here. The distance a ball rolls is directly proportional to the square of time. So the distance will depend on the square of time. But you can't forget the constant of variation. So that is what we are trying to deal with. The distance is equal to k times t squared. All right. Hopefully you're still with me. Now, what do I utilize this for? Well, this is not an equation relating the distance to travel to the time, because as of right now, I can't use k. K is just a random, arbitrary variable that we're using to represent the constant of variation. In this specific example, I have to know what it represents. What does k represent? I can find it on out by utilizing the brief description they gave me, because 8 feet go down, the ball goes down 8 feet once that first second is in the books. And so what this means is that the constant of variation actually equals 8 in this case. And so an equation that does, in fact, relate distance to time is that d equals 8 times t squared. Now we can utilize this information for any scenario representing distance and time in this particular example, just like in part B, where it says how far will that ball roll during the first 3 seconds. Well, now my goal is to find out how far it's going to roll when t equals 3. Well, doing some math on there, guys, we can see that 8 times 9 ends up giving us 72 feet. All right, so there's a perfect example of direct variation. We're going to continue this path, and the same thing holds true. And so we're going to see in this video a couple of direct variation examples. All right, but the same thing will hold true for inverse or joint variation. It's just identifying the key terms as to which one we're going to be focused on. So let's take a look. It says a gas law states that the volume of an enclosed gas varies directly. So once again, direct variation that we're dealing with as the temperature and inversely as the pressure. So we're dealing with both inverse and direct variation. So direct to the temperature and inverse to the pressure. The pressure of a gas is 0.7 kilograms per square centimeter when the temperature is 294 Kelvin and the volume is 8,000 cubic centimeters. Part A, write an equation relating pressure, temperature, and volume all together. Interesting. All right, so let's start on off here. Volume. Volume is going to be relating to the big picture when it is all said and done, because it says that the volume of an enclosed gas varies directly to the temperature, but inversely to the pressure. All right, well, let's go ahead and make V for volume. This is going to be part A. So V for volume. Well, what represents a direct variation? Well, a direct variation we know to be K times T, and I'm using capital T for temperature. We'll put capital T right there. However, it states that it goes inversely to pressure. So this represents a direct variation currently as it stands to temperature. But we have to also include an inverse proportionality to pressure. And so I'm using capital P for pressure there. Now, this represents our main function that we can use. But just like in the last example, we want to find out what that constant of variation is going to look like. So let's use the information they give us. They say the volume is 8,000 when, in this case, the temperature is 294 Kelvin and the pressure is 0.7 kilograms per square centimeter that we're dealing with. Well, now we're going to multiply 0.75 times 8,000 divide through by 294, and that's going to get us our constant of variation. And in this case, we get 1,000 over 49 when we simplify it on down. All right, so that is our value for K. So we are going to replace that in here, and now we know that 1,000 over 49 times T over P can be a useful equation that relates pressure, temperature, and volume for this specific scenario. Well, then it says use this information now to go ahead and to make some insight into a different scenario. Find the pressure when the temperature is 300 Kelvin and the volume is 7,000. So we already know what our constant of variation on is. And we just said that the temperature was 300 Kelvin, and we want to know what that pressure would be if this was the scenario that we are in fact given. All right, so just doing some quick math and simplifying on through, guys, we roughly get about 300 on over 343. And because the pressure is usually used in decimals, we're going to go ahead and simplify this on down to about 0.87 kilogram per square centimeter. All right. So guys, there's two examples that we looked into. One with specifically directly proportional. Two, one that incorporates both inverse and direct proportionality. Now give this one a shot on your own, and we'll go on over it first thing. We're on to the next one, guys.